Almost any discussion of quantum computing invokes some comparison to what is called classical computing. It's nearly impossible to talk about quantum computing without using the phrase, so we better start there. The term classical in classical computing is borrowed from conventions in physics. In physics, we often denote pre-1900 physics as classical and post-1900 physics as modern. Modern physics includes general relativity and quantum physics. General relativity is Einstein's theory of curved space and time, which explains the force of gravity. This theory, while instrumental in enabling us to comprehend awe-inspiring images of galaxies, has its most direct technological application in GPS. Yet, even this remarkable application is not standalone. It also requires quantum technology for accurate functioning. Quantum computing theory might have some things to say about places of extreme gravity like black holes. But we will stay grounded on Earth and won't say more about general relativity in this book. The reason is that, in contrast to general relativity, quantum physics has a broader range of applications that span diverse fields. It is the backbone of lasers and light bulbs, the lifeblood of medical scanners and radiation therapy, and the cornerstone of semiconductors and electron microscopes. It governs the precision of atomic clocks and the power of atomic bombs, among many others. And it is the fuel for quantum computers. The potency of quantum physics and its technological implications stem from exploring a new world, the microscopic world of atoms. By uniting three of the four fundamental forces of nature, quantum physics presents us with rules governing the basic constituents of matter and energy. The fourth force, gravity, while undeniably significant, is relatively weak, evident when we effortlessly overcome Earth's gravitational pull each time we stand up. The paradigm shift from classical to quantum physics propelled humanity from the era of steam engines and machinery to the digital information-driven age. Now it is driving us into the quantum age, the quantum in quantum computing. The story of quantum physics started in 1900 with Max Planck's quantum hypothesis. Planck introduced the idea that energy is quantized, meaning it comes in discrete packets, which came to be called quanta. The problem Planck was studying was dubbed the black body radiation problem. A black body is an idealization of an object that absorbs and emits radiation. It's a pretty good approximation for hot things in thermal equilibrium like the sun or a glowing iron pot, which give off roughly the same spectrum colors when at the same temperature. In other words, if you heat something up so that it glows white hot, it will be the same temperature as the sun, roughly 6,000 degrees Celsius. The problem was that no one could figure out why using the physics of the time, now called classical physics. As Planck was doing his calculations, he discovered that if energy has some smallest unit, the formulas worked out perfectly. This was a wild guess he made in desperation, not something that could have been intuited or inferred. But it deviated from classical physics at the most fundamental level, seemingly rendering centuries of development useless. So even Planck himself didn't take it seriously at first. Indeed, it took many years before others began to pay attention, and many more after that before the consequences were fully appreciated. Perhaps not surprisingly, one of those who did grasp the importance early on was Albert Einstein. Among his illustrious list of contributions to science, Einstein used Planck's quantum hypothesis to solve the problem of the photoelectric effect. The photoelectric effect is a phenomenon in which electrons are emitted from a material when exposed to light of a certain frequency. Classical physics could not explain why the energy of these ejected electrons depended on the frequency, color of the light, rather than its intensity, brightness, or why there was a cutoff frequency below which no electrons were emitted regardless of the intensity. Einstein proposed that light itself is quantized into packets of energy, which later came to be called photons. Each photon has energy proportional to its frequency, in accordance with Planck's quantum hypothesis. When a photon hits an electron, if its energy determined by its frequency is sufficient, it can overcome the energy binding the electron to the material and eject it. Quantization had taken hold. This marked a profound transition in physics, which is still the source of confusion and debate today. Before photons, light was argued to be either a wave or a particle. Now it seems that it is both, or neither. This came to be known as wave-particle duality. Until this point, quantum theory seemed to apply only to light. However, in parallel with these developments, experiments were starting to probe the internal structure of atoms in ever more detail. One curiosity was spectral lines. Specific lines or gaps were present when observing the light that the purest forms of elements, hydrogen, helium, lithium, and so on, emitted or absorbed. Many formulas existed, but none could be derived from classical physics or any mechanism until Niels Bohr paid a visit to England in 1911 to discuss the matter with the leading atomic physicists of the day. Bohr's model proposed that electrons in an atom could only occupy certain discrete energy levels consistent with Planck's quantum hypothesis. When an electron jumps from a higher energy level to a lower one, it emits a photon of light with a frequency that corresponds to the difference in energy between the two levels. This model provided a way to calculate the energies of these spectral lines and brought the atom into the realm of quantum physics. He presented the model formally in 1913. A decade later, Louis de Broglie proposed in his PhD thesis that not just light, but all particles, including electrons, have both particle and wave characteristics. This was a revolutionary idea that was quickly put to the test and verified. At this point, it was clear that quantum theory was more than a technique that could be applied as corrections when classical physics didn't fit the data. Scientists started to theorize abstractly using concepts of quantum physics, rather than turning to it only as a last resort. In 1925, Werner Heisenberg invented matrix mechanics to deal with the calculations underpinning the theory. Using it, he showed that it is impossible to measure the position and momentum of a particle simultaneously with perfect accuracy. This uncertainty principle became a fundamental and notorious aspect of quantum theory. At the same time, Erwin Schrödinger developed a mathematical equation to describe how de Broglie's waves might change in time. The variable in the equation, called the wave function, describes the probability of finding a particle in a given location or in a particular state. In contrast to matrix mechanics, Schrödinger's picture was called wave mechanics. There was a brief debate about which of the two alternatives was correct. However, Paul Dirac showed that both are equivalent by axiomatizing the theory, demonstrating that a simple set of principles can derive all that was known about it. He also combined quantum mechanics with special relativity, leading to the discovery of antimatter and paving the way for further developments in quantum field theory, which ultimately led to the so-called standard model of particle physics that supported the seemingly unending stream of particle discoveries in high-energy particle accelerator experiments. However, by the middle of the 20th century, quantum physics was more or less a settled science. The applications of the theory far outstripped the discoveries, and the majority of the people using it resembled engineers more so than they did physicists. We'll get to those applications briefly, but first we need to jump ahead before jumping back in time. During the 1960s and 70s, engineers in the laboratories of information technology companies like Bell and IBM began to worry about the limits of the new communications and computing devices being built. These things require energy to function, and energy is the primary concern of physics. Did the laws of physics have anything to say about this? And if they did, wouldn't the most fundamental laws, quantum laws, have the most to say? Indeed, they did. And this is where the two theoretical fields of physics and computing converged. But to appreciate it, we must tell the other half of the quantum computing backstory. Often in quantum physics, it is useful to compare the results of some theory or experiment to what classical physics might predict. So there is a long tradition in the quantum versus classical comparison. This tradition was adopted first not by computer scientists or engineers, but by quantum physicists who started to study quantum computing in the 80s. Unlike in physics, the adjective classical in classical computation does not mean it is pre-modern, it is just a way to distinguish it from quantum computation. In other words, whatever quantum computing was going to be compared to, it was bound to be referred to as classical. Abstract computational theory, now referred to as theoretical computer science, was born in the 1930s. British World War II codebreaker Alan Turing devised a theoretical model of a computer now known as a Turing machine. This simple, abstract machine was intended to encapsulate the generic concept of computation. He considered a machine that operates on an infinitely long tape, reading, writing, or moving based on a set of predetermined rules. Remarkably, with this simple model, Turing proved that certain problems couldn't be solved computationally at all. In 1945, John von Neumann expanded on Turing's work and proposed the architecture that most computers follow today. Known as the von Neumann architecture, this structure divides the computer into a central processing unit, CPU, memory, input devices, and output devices. Around the same time, Claude Shannon was thinking about the transmission of information. In work that birthed the field of information theory, Shannon introduced the concept of the bit, short for binary digit, as the fundamental unit of information. A bit is a variable that can take on one of two values, often represented as 0 and 1, which we will meet again and again in this book. In his work, Shannon connected the idea of information with uncertainty. When a message reduces uncertainty, it carries information. The more uncertainty a message can eliminate, the more information it contains. Shannon formulated this concept mathematically and developed measures for information, realizing that all types of data, numbers, letters, images, sounds, could be represented with bits, opening the door to the digital revolution. Nowadays, the concept of a bit underlies all of digital computing. Modern computers, for example, represent and process information in groups of bits. Fast forward to the 70s, and the field of computer science was in full swing. Researchers devised more nuanced notions of computation, including the extension of what was computable to what was computable efficiently. Efficiency has a technical definition, which roughly means that the time to solve the problem does not blow up as the problem size increases. A key word here is exponential. If the amount of time required to solve a problem compounds like investment interest or bacterial growth, we say it is inefficient. It would be computable but highly impractical to solve such a problem. The connection to physics emerged through what was eventually called the extended Church-Turing thesis, which states not that a Turing machine can't merely simulate any physical process, but that it can do so efficiently. Today, all computers have roughly the same architecture. A single computer can do any computational task. Some problems are hard to solve, of course. But if you can prove it is hard to solve on one computer, then you know there is no point in trying to design a new kind of computer. Why? Because the first computer can efficiently simulate the new one. This is what the extended Church-Turing thesis says. It seems like common sense to the modern digital citizen, but is it true? Maybe not. When we think about simulating a physical process based on quantum physics, it appears that a digital computer cannot do this efficiently. Thank you so much for joining today. See you soon again. Until then, keep dreaming big.